Hello, and welcome to today's webcast brought to you by Lightwave. Today's event, Optical Return Loss and Reflectance, will be presented by myself, Larry Johnson, and the event is sponsored by the Light Brigade. But there's a few questions we want to ask before we start to cover a few housekeeping items. You can expand the slide area by clicking on the maximize icon on the top right of the slide area or by dragging the bottom right corner to enlarge. In fact, if you can expand and reposition many of the components on your screen, so please feel free to arrange as you desire for your optimal webcast viewing experience. At the bottom of your audience console, there are multiple application widgets that you can use. If you have any questions during the webcast, you can click on the Q&A widget and submit your question. We will try to answer these questions during the live Q&A portion at the end of the webcast. If you experience any technical difficulty during the webcast, please click on the Help widget. It has a question mark icon and addresses common technical issues. If you still need assistance, just type your issue into the Q&A widget and a member of our webcast support team will work with you to correct the problem. Any additional resources for this webcast can be downloaded via the resource list widget that looks like a green folder at the bottom of your screen. For your convenience, this presentation will be available on demand within 24 hours of this live event, and a reminder email message will be sent to all registrants with a link to the archive, and it will also be accessible from the Lightwave homepage. So, with that, let's go on to the next slide. A little background about the Light Brigade. We've been doing fiber training since '87, and it's always fun to stay current with a really exciting technology. And I know many of you are sitting in here. Many of you have been putting in fiber optic systems for ages and that, and others are new. So we're going to try to address this from the novice to the journeyman level, and also from different perspectives, from manufacturers to end users. So the objectives for today is to summarize what optical return loss is, explain reflectance and its causes, discuss the impact of optical return loss and reflectance, and explain how they affect signal quality. We also want to show options to minimize or decrease ORL and reflectance, and also, of course, we always have to address the test and measurement issues. So first, lasers are affected by optical return loss and component reflectance. Now notice I separate these into two areas, and we'll expand on this as we progress, but optical return loss is the total reflectance of the entire fiber span, where component reflectance is just that. It's an individual item that's reflecting light. So when you hear the term reflectance, it's component. When you hear the term optical return loss, it's system. And where we start really seeing these effects is when we get systems operating at 10 gigabits or greater. And any analog system is affected by reflections. And while we're going to talk about some of the system standards that are out and who provides these systems toward the end of the session, I just want to remind everybody that system manufacturers specify ORL values that are required to assure the quality of signal performance. So in other words, if they're saying they're going to operate at a given bit error rate, that number depends on the values that they give. So while we can give you what the test standards are, you do have to pay attention to the manufacturers and their specifications, making sure that your installed fiber plant meets those values and that. So. And the bottom item was we were talking especially the role of connectors. So a couple things here. We're going to have a few animations we're going to show, but I'll talk about it first, then we'll run the animations going through. Actually, in this case, let's go ahead and start with the animation. So this is a Rayleigh Backscatter, and it's caused by molecular and optical impurities introduced during the manufacturing process. And this causes energy to be reflected in all directions, including back to the optical source. And Rayleigh Backscatter is one element of optical return loss. So when we talk about the fiber's reflectivity, it's this intrinsic backscatter that's causing that. And this same technique is what's used by OTDRs to actually measure attenuation backscatter, because OTDRs work on the theory of Rayleigh Backscatter. So the term ORL which is, as I said before, is the sum of the reflections in an optical path or in a fiber link. And these reflections include both intrinsic, in other words, the fiber, and then extrinsic, which would be connectors and mechanical splices, passive device such as optical splitters, WDMs, and those type of components. And the largest reflections are caused by Fresnel reflections, where there's abrupt optical transition, such as a connector, which is glass to glass or glass to air to glass in the worst case. And so the reflection, and again, we're going to show the animation here and show what happens to the laser cavity. Then we'll step back a little bit. So what I want you to see here is a pulse going down the fiber, and then when there's an abrupt change, that energy comes back, and it disrupts the lasing function of the laser. Let's go back one slide so they can see the text here. So the light's returning to its original material when it encounters the interface of two materials with different refractive indices. And again, these are called ORL because it's the sum. It's not. We do have the reflectance of a connector, but the system's affected by the sum as well as the individual. And the return loss is measured in dB. But I want to talk a little bit about this value down at the bottom, because if it's caused by a component, and let's say that it's in a fiber to the home system, and in this case, the reflected light, say that there's a connector and it's dead-ended, so it's pigtail spliced on, but there's no connector mating up to it, which means that that's a glass-to-air reflection there. And that's a very high level, in this case about the minus 15 dB. But this is a connection point that's 20 kilometers away. That means that that reflection has to come 20 kilometers back upstream to the actual laser transmitter. And assuming a loss of averaging 0.5 dB per kilometer, this would give us 10 dB of fiber attenuation between the component that's causing the reflectance and the actual laser. So the amount of reflected light received at the laser would be minus 25 dB versus the minus 15 at the actual component. So we'll go up a couple slides here. And we'll talk about Fresnel reflections. Again, these are the abrupt. These are the Fresnel reflections are the major cause of reflectance problems. And if a component will not pass a Fresnel reflection value, that means your optical return loss value will be directly affected, and it won't pass ORL as well. But let's talk about Fresnel reflections here. So there are abrupt changes between the fibers. It could, even a physical contact fiber, a UPC or APC, still going to reflect some optical energy. It's an abrupt transition. And that worst case, though, is glass to air. And normally you'll get these at patch panels to where you've spliced the end connector on, but it's not connected with a patch cord to the receiver. And even if it was connected with a patch cord, between the receiving connector and the photodetector, there's another air gap there. And so it would cause an abrupt Fresnel reflection. And these affect the operation of the laser. So let's look at the animation on this one. So while most of the optical energy passes through the connection, a percentage of this is reflected back. And this is why it's important that we follow certain polishes on connectors, certain cleaning procedures on connections, etc. So what is reflectance? It's the percentage of light reflected by a single component. And the biggest cause of these are connectors. And the closest connector at the patch panel and the farthest end connector are the ones that we'll predominantly be talking about or concerned with the closest one being the biggest problem, and we'll show that soon. But look for open connector ports. In other words, if it's not mated, that means there's a glass-to-air interface there. And we will give you a solution for those in case you're having Fresnel reflection problems. Contaminated connections as well, because the contaminant can also increase the reflectance. And with high-speed systems and DWDM systems, these can get extremely sensitive to the cleaning materials, and in some cases may only affect 1 or 2 wavelengths instead of all of them. So we have to really pay attention to the cleaning procedures. And again, many of the high-speed manufacturers give very precise procedures on the types of cleaning products they want used to make sure that you're obtaining the bit error rate and the quality of signal. Also, a couple other components. Remember, mechanical splices are reflective, and any lensed components are reflective as well. Okay, so again, what is reflectance? One high Fresnel reflection can cause a span ORL value to be out of spec. That's where we're going to be testing to identify not only the optical return loss of the fiber span, but also which component is causing the ORL to be out of spec. And that's key, so therefore the understanding and operation of the OTDR is critical. And the third bullet where we say limits may occur due to the dead zone of the OTDR, that's because of the pulse width of the OTDR is longer or greater than the distance between the transmitter's connector port and the patch cord to the patch panel. And the most common term used for this is dead zone box, which is a length of optical fiber that would allow us to operate within the limitations of the OTDR. Now, to be a little more specific, the TIA 455 standard, which includes all the fiber optic test procedures, or FOTPs, three of them in particular, FOTP 59, FOTP 60, and FOTP 61, define that the minimum dead zone box for an OTDR should be 20 times the minimum pulse width of that OTDR. Now, because most operators don't know the pulse width of their OTDRs, what the industry does is pretty much package these pulse suppressors, fiber ring, dead zone boxes, many terms used, to be in increments of 100 meters or 500 meters or 1 kilometer, and that instead. But technically, it has to be 20 times the minimum pulse width of the OTDR to be able to get around the Fresnel reflections at the first cross-connect panel. Now, remember that what these reflections affect is the light source itself. And in this case, LEDs are not affected by reflections, and the vertical cavity surface emitting lasers used in multi-mode systems are very insensitive. Well, what this means, though, is the two dominant types of lasers that are used with single-mode systems, the Fabry-Perot and the DFB lasers, are affected by these. And remember that the acronym LASER, light amplification by stimulated emission of radiation. And what happens is the light feeding back into the cavity of the laser disrupts the laser's operation. And these two laser types are extremely affected by reflections and that. So there's two types of modulation. We'll show animations on those soon enough. And we'll also talk about an optical isolator and that. So let's go to the next slide here. And so to be more specific on the effects of the laser, all single mode lasers are susceptible to reflections, and that the VCSEL used in multimode again is insensitive to this. And so what we're doing is we're disturbing the optical wave in the laser cavity, and that increases the noise floor of the laser. And the Fresnel reflection in particular, hit the wrong button, cause reflections become unstable. And so this degrades the RIN or RIN performance, and which causes instabilities and increases the effective noise output of the laser. And that, so what we want to do is try to find a solution for these. And that solution depends on the type of laser that's going to be used. Now, DFB lasers are more costly. They have much narrower spectral width. They're used in DWDM systems. They're used in cable TV systems. But they're also used in virtually every system that's at 10 gigabits and higher. But they also have the greatest sensitivity to reflection. So what happens to manufacturers, and from the component level to the subassembly level to the system level to the user level, 4 different levels in fiber optics, and that so if the system manufacturer knows that they have to meet a certain optical return loss threshold, they may find that they're going to order their DFB lasers with optical isolators, which work as optical valves, which allow light to pass through in one direction but not in the other. and they'll order these to be in with the DFB. However, most users don't know if that system has an isolator in it or not. So it's always a good idea to talk with the manufacturer, take a look at their specifications, and make sure that you can meet those values. And that, if not, then we have to find solutions on reducing the reflective events. Okay. The modulation of these lasers can also change. So we have direct modulation, which we're using typical on-off keying functions where the laser itself is being turned on and off. Unfortunately, this introduces chirp into the signal, but it is less expensive to do so. So, when we talk about analog signals versus digital signals, just some quick comparison of the two types. For example, for an analog system, we're limited to DFB lasers and LEDs. They're the only two sources that do not create noise problems by themselves inherently. On the other case, for digital, we can virtually use any of the types of sources, including the vertical cavity surface emitting laser, which isn't listed here. The detector is also critical on a avalanche photodiode, which increases the optical gain and or the quality of the signal at the receiver. That also amplifies noise, and which is we don't like noise in analog because analog looks like noise. So the positive, intrinsic, negative type photodetector has to be used on analog signals. The connections. Depending on the level of the signal and the quality of it, we're still using low reflectance connectors, the physical contact spherically polished connector, the ultra physical contact polish, and also the angled physical contact for those. And of course, on digital, all types can basically be used, but PC levels at a minimum. And we'll talk a little more about the different types of polishes and the reflectance of these. Also, that most analog systems will be fusion spliced, which is a non-reflective event versus a mechanical splice. So going back to the optical isolator, so they work as optical valves. They reduce or eliminate reflections with up to a 50 dB reduction. They're most commonly packaged with DFB lasers to reduce the effects of ORL and Fresnel reflections. And again, packaged with DFB lasers, the most common. And again, we're seeing an individual component here with a 900 micron fiber, but these can also be packaged in the laser itself as an optical subassembly. So let's look at the impact of the components. And remember that the closer the component is to the laser, the greater the impact is to the laser's transmitter. So we'll look at the first one here, and we'll see that it's the connector that's actually on the transmitter card itself. Now remember that the manufacturer knows the laser, they know its characteristics, and so they're specifying a connector type for the mechanics, but they're specifying the polish for the amount of reflectance that component's going to cause. Now if we go to the second event, this would be the patch panel, and again, this is at the end of your jumper, and this is where you're cleaning in particular. What comes in, we need the cleaning at the transmitter and receivers as well, but most people will be handling connectors at the patch panels, and therefore there's more of a tendency to have connectors contaminated here than there would be in the transmission equipment itself. But again, it's the second closest event to the transmitter. So let's go to the third event here, and in this case, it could be an outside plant connector, but in this case we're showing a fiber optic splitter such as would be used in fiber to the home applications. Well, you do have an input connector prior to the splitter, and you have a variety of output connectors depending on the split ratio. And again, the distance to these as well would be impacted. And if we go to the fourth item, we can see the far end patch panel. And remember the calculation we did before that says regardless of the reflectance of this, there's a certain amount of attenuation that signal will have to get all the way back to the transmitter. And so we can, even if the connectors would be out of spec for that one direction, the actual attenuation of that reflectance may make it pass in that direction. Of course, the opposite direction, now you're closer to the transmitter running the opposite direction. And the last point is actually the connector at the receiver, which again can cause reflectance. And there's two cases here where in one case the reflectance can go all the way back or return to the original transmitter, but on the other case, the Fresnel reflection between that connector in face and the one at the preceding patch panel, the item number 4, we can start getting echoes in that in here where the reflectance is beginning to echo in here, and then still be recovered by the receiver, and that can cause a signal quality problem as well. So what should we look for in connectors? And the question I ask everybody is reflectance more important than attenuation? And in the early days, we weren't worried as much about reflectance as we were attenuation, so there was more of a tendency to specify values and the amount. But attenuation does affect the bit error rate or signal quality of a connector, but so does reflectance. So it's a question each organization has to ask themselves. So, I put the two common values of connectors down, one specified by the ITU's G.671 passive optical component standard, the other by Telcordia's GR326 recommendation of 0.4 dB. But the reflectivity values change too, and the Telcordia GR326 specifies 55 dB for the UPC polish, 65 dB for the APC polish, but they also, I'm going to take us back a few decades here. Many of you that remember the first years when we put fiber optics in, that the first polishes in the late 80s, early 90s was a PC polish, which was 40 dB, and then later there was the super PC polish of about 50 dB, 45 to 50 dB. And the reason I'm bringing this up is many of you are operating legacy systems that still have the original patch panels and connectors that were installed in the early days. Those connectors may not pass the values that are required today. Of course, you could re-splice those, put new pigtails on or connectors. Now with splice-on connectors, it makes it a lot easier with APC and UPC polishes. Or you could do a retro polish, because there are retro polishers in the industry to take a connector and repolish it. But it's these older systems. At the same time, there's some values here that we didn't cover, and these go to the IEEE 802.3 standard and the TIA 568 standards. And these are written really more for multi-mode than single mode, which means these values are not used because of the types of lasers. And even though the 26 dB for single mode is specified in both these standards, with a Fabre Pro or a DFB laser, unless it had an isolator, it would not pass that value. Okay, so again, here's your polishes, and that from the original, the single mode polishes, and then the multi-mode. And by the way, the PC and the SPC would look the same as a UPC. It may have the blue housing on. I remember some of them had red housings way back. But if you look at the reflection level, and then you look at the percentage of the light that's reflected, we're dealing with a very minute amount of the signal being returned, and that's where, when you look at, say, fiber to the home cross-connect panels, they all come with APC connectors, and the reason is the manufacturers of the cross-connect products, they don't know what type of signal you're sending, whether it's an analog signal, whether you're a digital signal. So they're putting the APC sleeves into these panels, assuming that everybody's going to put APC connections in. However, for many of you that are in digital systems only, you can use UPC, but again, check with your manufacturer specification to verify that. And also there's some values down at the bottom for multi-mode polishes. Again, reflectance is not an issue for those. Yeah. So there's also the case of contamination, and it has a impact on reflectance as well. And so we know that the causes, whether it's a scratch, is it in the mode field diameter or the actual light transmission area of a single mode fiber, or is it in the cladding? A scratch in the cladding shouldn't affect us, but a scratch in the mode field diameter definitely could. It does refract light. Contamination also, there's different types of contaminants, and based on the type of contaminant, the size, the physical size it is, and the width and the depth. And the reason depth is important because it creates a separation between the two glass interfaces. So then you have a glass-air glass interface, which again is highly reflective on that. So in one case, if we can clean the contamination off, that's excellent. We don't want it to cause damage because then we get into a maintenance or repair mode. We do need to know the location of it and the type of substance for proper cleaning. But there is an impact to these, and whether it's damage or separation, they still cause an increase in reflectance. Now the IEC and the TIA have both issued standards that specify acceptable parameters for cleanliness and or damage. The two standards do not duplicate each other, but they complement each other, so they are good standards to order and review. But remember that in this case, connectors, we're talking about Fresnel Reflections, not Rayleigh Backscatter, and any physical separation is going to increase the reflectance of it, and it's going to certain types of cleaning products such as isopropyl alcohol, which are not recommended for use with laser products. So today what you want is really to reduce reflections using the right cleaning product. It's that critical at any connection point, and also, as I mentioned before, the manufacturers have products that they recommend as well. And here's some diagrams from the IEC inspection standard that just shows a good connection, ferro end face, I should say, versus those that are caused by contaminants, which can be cleaned, and those that are damaged, which need to be repaired for them. So the nice thing with these standards is they do give you causes and examples to use from, and the nice thing today with digital scopes is that we're able to store pictures if needed, send them for evaluation if needed as well. Now I want to talk about a solution, and these are called optical terminators. Optical terminators are basically a single mode plug that has the same end face geometry as whatever your network's using, so whether they're SCU PCs or SCA PCs as shown. You can see in the technician's hand a terminator. It looks like just a plug without the cord. The difference is it matches the end face, so we have a glass-to-glass mating condition. But beyond that, the pre-polished glass inside there's several methods of making these. There's what's called a Z-splice. You can fracture the fiber as a second one, but you dead end the fiber inside these so that there's no reflectance on the end of the fiber. The only reflectance is the actual end face matching up with the connector and the polished type that's under use. So these can be used to, if you have open ports, you can buy these and just you clean them first, of course, and then you just plug them into those ports, and they will reduce the reflectance substantially based on the polish type you specify. The other one is when you're running OTDR tests and you actually want to know what the reflectance of those connections are. You can use the Terminator to test by mating them up to them. Just make sure you're always cleaning, mate, and of course now you're taking an OTDR operation from a one-man operation to a two-man operation. But we're going to need to do that with one of the alternatives, which is the use of dead zone boxes anyway. So just a brief overview on what an OTDR is and what it does. In that it measures the fiber length, it measures distance in general to any kind of fiber events. That could be a splice, could be a splitter, could be a macro bin, a micro bin, a break in a fiber. It does measure reflectance of components, and it also measures optical return loss. Remember, the OTDR is based on the theory of Rayleigh Backscatter. It measures loss as both dB for components, but also dB per kilometer for spans. And it measures splice losses. You can use it to monitor fiber spans and also for your system documentation. What we want to do is use the OTDR properly to measure reflectance as well as measuring attenuation. So the reflective signatures include the connector, the mechanical splice, the end of the fiber, also the start of the fiber, and any lens component. And here we see an example where one splice was highlighted, but now we're on to the next one, which is okay because I can talk a lot more about this one. Excuse me for a second while I take a sip of water. Okay, if you look at this, I see a couple things. At the far left, there's actually a Fresnel reflection up against the left side of the graphic. And then as we continue down, we see some non-reflective signatures caused by microbends, macrobends, fusion splicers, a slight Fresnel reflection at the angled PC connector, or the APC. And then we see a PC connector, a standard connector, and a cleaved fiber end. So you notice that the greater the reflectance, the greater the spike. Little caution here. On all OTDRs, length is measured on the bottom horizontally, and dB is measured vertically on the side. Never use that dB scale to measure the reflectance of a connector, because we had to suppress the Fresnel reflections to have them fit on the screen because the OTDR is so accurate. So it gives you a visual indicator, but do not use the dB levels on the vertical scale as a comparison. But what you can see here is the higher the reflectance or the spike, the higher the reflectance, and again, the lower the reflectance, such as the angled PC, that's desirable. Okay, let's continue on. Here's a couple, an example of two different, it's the same connector. One of them's just showing at a patch panel, it's a glass-to-air interface on it, and that's roughly 15 dB. But the far right has a terminator put onto it, and so instead of being minus 14.89 dB, it's minus 40.03 dB. So that's using an optical terminator. So we've suppressed the reflectance of that far end connection there. Some other signatures that reflectance causes, since we're talking about OTDRs, is ghosting. And that technically a ghost is an echo, and that between two highly reflective events. So if we take a look from the far left up against the grid, we'll see the first Fresnel reflection, then the cursor A is put on the second Fresnel reflection, and that's causing an echo, which is marked by the B, but we call it a ghost, but technically it's an echo. You can also see where there's another one at the far right side and you can see again, these are all equal distance for them. Let's go to the next slide, and we can tell you another event on ghost. Ghost signatures, because they're just echoes, they have no loss in that form. So if you don't know if it's an actual connection or not, one of the trends is they're equal distance from a prior reflective event, number one. Number two is they have no loss. Okay. And just on this one, you can see another case where there's a ghost reflection at the far end to the far right. Okay. You can also see that there's been two dead zone boxes put into this test. So each of them are probably, say, 1 kilometer each. So we have from the screen from the initial Fresnel reflection against the left side. And then event number 2 is the end of the first dead zone box. The span is in between 2 and 3. And then the far end dead zone box. Now the reason that this is advantageous is it allows you to measure the reflectance at each patch panel as well as the attenuation. Without a dead zone box, we would not be able to measure the loss through those connectors, and of course that's combined. If you had a pigtail splice out, that loss would be combined because the pigtail is normally so close to the connection that it's within the OTDR's dead zone. So again, the standards call out the use of dead zone boxes, and the IEC standard in particular calls out the use of a dead zone box at the front and far end. So it is a way to get accurate measurements using the OTDR. So you do have two choices, and that one of them is to do exactly what we showed before, which is the use of a dead zone box on the front end, another one on the far end. Therefore, your measurable fiber length is in between them, and now we can measure attenuation through those connectors as well as the reflectance of those connectors. On the other case, if you wanted to use one dead zone box and use a terminator at the other end, you could. The penalty on this, though, is you don't get the attenuation at the far end connection, but you do get the reflectance at the far end connection. Now, beyond the OTDR, there's instruments that actually are designed for measuring reflections that are more accurate, because do remember that the OTDR is a theoretical instrument where any type of measurement equipment that requires calibration is a known value. So reflectometers, continuous wave reflectometers, back reflectometers, they're more accurate than the OTDR. They do require calibration. They can give you far more accurate return loss values in that. And potential system problems, again, the nature of analog signals using a laser, and also high bit rate systems as well. And what you're seeing here intrinsically with the schematic is the fact that we put in an optical switch and an optical splitter so we can compare input versus output measurements, which is what's defined on measuring reflectance. The other thing that the test equipment manufacturers depend on is the use of standards that define how the measurement will be made, and the other one is how to use it and the values, and therefore the test equipment can be manufactured to test to different standards. So I listed a few of these from the TIA, the 455 FOTP-8, FOTP 107, two IEC standards, one test measurement and system, the other talking about communication subsystem testing, and how to work with dead zones and suppressing Fresnel reflections. And that. Other system standards, in this case, the IEEE, the 802.3 standards, the BA standard, which accounts for the 40 gigabit and 100 gigabit Ethernet standard, again, gives us the lower end values for multi-mode and single-mode fibers. I'd be very cautious of that 26 dB value. I would definitely talk more with the system manufacturer and seeing what value they specify versus the 26. The different fiber to the home standards, the G983, 984, G987, and even G989, these are the legacy PON systems, the 10G PON systems, and the newer WDM PON system standards. These will also provide values in both the upstream and downstream direction as well. The OTN and the SONET standards, G.957, that relate to the Synchronous Digital Hierarchy Standard, SONET for North America, also has an optical return loss value. Again, you can look at the terms. If are they saying ORL or are they saying reflectance here? And then the structured wiring standard, the TIA 568 standard, and it's actually in the C.3 subcomponents version of that standard, has different values as well. So what we have here is just making sure that everybody understands the importance of reflectance and optical return loss. And the major impact is to the laser itself, and they're extremely sensitive to Fresnel reflections. And the direct impact is the bit error rate or the quality of signal of a system. And it causes this by the instability that the laser incurs by these types of reflections. The second point is that testing for reflectance and ORL should be a standard part of your outside plant testing. And unfortunately, we haven't spent as much attention on reflectance as we have attenuation. But as speeds continue to increase, we're going to see more critical concerns with the measurement and making sure that these components are going to work to specification. And again, for all those that have the older single-mode systems, remember that you were dealing with PC polishes and SPC polishes. It's only since about 2000 that we dealt with the UPC and the APC with polishes and that for it. So we're going to have time now for some Q&As. And also just a little note, we have two DVDs, only one's listed here, that talk about testing optical return loss and reflectance. One of these is called OTDR Theory and Operation, and the other one is Fiber Optic Test Equipment, Testing Fiber Optic Length, and there's a special price if you want these in that form. But they're very unique. They show you how to do the testing and that, and we'd appreciate it if you take a look at them for that. So let's go ahead and look at some of the questions here. And let's see. Okay, let's go to the, okay, I can't see the entire, okay, describe the purpose of power meter testing. Okay, power meter testing is basically just attenuation testing, and that, so we can, and power. So we can measure the output power of a transmitter, and we can measure the receive power at the receiver or anywhere where there's a connection. In that case, we'd be testing in the dBm mode, in other words, a power measurement versus an attenuation measurement. If it was for attenuation, we would zero the meter and then just measure dB. More enhanced optical loss test sets give you the ability to measure reflectance as well, and that for it. Okay, so the another question here is, what's the optical return loss for multi-mode fiber? With the IEEE B.3 standard specifies it as 20 dB, and remember that an air gap would be of roughly 15 dB. So we are having physical contact. So if you were using old multi-mode connectors such as SMAs, going to the dark ages here, those are air gap connectors. So today, STs, SCs, LCs, those are all physical contact. Let's see, there was a question here. We're having fun here. There's a lot of questions, so I'm trying to address them all. So, okay, what are the typical wavelengths affected by older fiber? Well, it depends. The oldest fiber, single mode, was originally designated as 1300 nanometers. It wasn't defined as 1310 until the late 1980s. But it would definitely be the 1310 and even the 1550 nanometer wavelengths. So those would be the two in particular that you're looking for. Okay, two. So I don't know if these are coming in. Let's start at the bottom because the time's inverted. Okay, there. Okay. So let's see. Only ORL. Well, ORL affects, there's a question here about the speed of the 10 gigabits and it says that there's a greater sensitivity to optical return loss and reflectance at 10 gigabits per second, but you need to know what the system manufacturers are and that for it. Okay, and then I have an assistant here, so I'm going to just, if we can click on when they're answered, it may be a little easier, but we'll work our way up through these. Okay, there is a question here that the percentage difference between a APC and a UPC connection, and it's about 10 dB. So in other words, a APC has 1/10 the amount of reflectivity as a UPC connection would be as well. And there's a question here on, can APCs be connected to a PC connector? They could, but you don't want to. The increase in reflectance, because one's angled and one's physical, you would end up with an air gap and the reflectance would be atrocious. Not only that, but the directional loss through that connector would be as high as 5 dB. So you don't want to intermate, and that's one of the reasons we color code the green for the APC and the blue for the UPC, is that we don't have that occur. A question let's see, what about a fiber to the home situation where not all the connectors from a 1x32 splitter are plugged into a patch panel, but are all lit? It would be the case is here is you would have the Fresnel reflections on the open ports. You'd have them on even the mated ports, but the critical ones would be the open ports. And depending on how far away that splitter is from the transmitter, the optical line terminal, you would have you'd have the attenuation coming upstream based on the distance for it. But you also have to know whether you're sending an analog or digital signal. So if it was running an RF overlay system with a WDM, you would probably have to put terminators on those open ports because you are overlaying a more sensitive analog signal on top of a more friendly digital system. Okay, a question on the difference between reflectance and back reflection. Reflectance is the component itself, and that back reflection is the amount of measured light at the transmitter. and that. So it's so the reflectance, if you use an OTDR and you measure it and it's 20 kilometers away, that's saying, okay, the reflectance on this is minus 50 dB, but yet 20 kilometers up, it's 10 dB lower, so instead of 50, it would be 60 dB because the amount of light that the laser would actually see. And okay, question, can high optical loss cause slow internet speed? Definitely. Because whether attenuation, dispersion, or reflectance, and remember those are the three critical elements that you're dealing with in a design of a system: the signal loss, the signal dispersion, and the reflectance. All three of those can affect the quality of the signal. So in that case, we don't, it can impact it because whether it causes latency, you have to resend information. It will slow down the system. So it can. I would have to know more specifics on it. There's a question, do we have an example of an OTDR trace that shows a Terminator installed? We did show one. If needed, I can resend that back to whether we showed a comparison from one to the other, and there was a difference of about 25 dB through that Terminator. A question on how the defects in epoxy and cladding zones affect light transmission. Well, because it's not in the core area or the mode field diameter, it shouldn't directly affect reflectance. However, if you're getting problems, now you're getting into connector tolerances and fiber tolerances and the centering of the fiber. And we have an online tutorial called Light Bites. It's on single mode fiber in theory, and it goes over each type of single mode fiber and each type of tolerance that's affected. It'd be a great one to show, so if anything, I'll get back to you on that one for it. Let's see, which is a normal value of optical return loss for a point-to-point link? Normally we're in about the 30 to 35 dB range for ORL, and that for that. Remember that that's a sum of the fiber and the reflectance of all the components as well, connections as well. Another question, how does the Terminator help in OTDR testing for optical return loss? Well, because the Fresnel reflection of any open port does affect ORL, the Terminator, by using two Terminators, it will improve your ORL values because the Fresnel reflections will not degrade those values. And boy, hitting these. What are the most common causes of ghosting events? The biggest one is an air gap, and that because it has the highest reflectance. But it could also be a case where you have because of the polish on the connectors themselves, and so that's why we want to use UPC and APC polishes on our connectors, is to minimize those where we shouldn't see the ghosting occur on that port. What you could be getting into a case is you may have older polishes, say the SPC to a newer UPC, and you're going to take on the characteristics of the older polish and that instead. Let's see. There's a question about specific brand of cleaning products. I'll take that offline and now this. And the reason that I don't want to talk about specific vendors, that's not our role in training. But there are specific types of cleaning products that are used, and we can address that again offline. Let's see. What was the optical connector piece called that helps with the ORL corrections that keep it in range? I believe we're talking about the optical terminator, because once it suppresses the Fresnel reflections, the optical return loss value should come within spec. Okay, how much Fresnel reflection is acceptable when one has two different generations of fiber? Interesting question, because I would need to know more about the types of fiber, whether it's a G.652 fiber or a non-zero dispersion shifted fiber, a dispersion shifted fiber. But a Fresnel reflection is still a Fresnel reflection. It shouldn't matter based on the type of fiber or the generation fiber. But I think in this case, we'll talk by email and try to get a little more understanding of what we're covering there. And here's a question, do we have an example of an OTDR trace that shows wavy fiber? That would be a concern to me if your fiber should be, your backscatter trace should be really in a linear line, and it shouldn't be increasing or decreasing. And if you imagine this, that means that your attenuation is not constant over that fiber span. And so the case then is saying, what would cause that disturbance in the fiber? Are we seeing a buffer tube collapsing? Are we seeing a cable that was improperly installed? I'd sure like to see an original OTDR chart on that fiber before, when it was acceptance tested, so that we could discriminate whether it was caused by the manufacturer or the installation. But we definitely should not see a wavy waveform. Okay. When troubleshooting optical return loss on a DWDM amp, do you have to troubleshoot on the input or output port of the amplifier? This is a really good question. It's a very complex question, so I would need to know a little more information on this, because I'm a little concerned, because you're operating with a DWDM system and you're operating an OTDR, and the OTDR, by not knowing the center wavelength and the spectral width of the laser, you could be disrupting multiple lambdas on the system. So I need to have a little more communication on that. So we'll talk with that one offline. Can you be receiving normal light levels and port ORL at the same time? Definitely. And this is one of the big problems, is because when we're looking at light levels, we're looking at optical power. And remember, early on I was saying, what's more important? Is it attenuation or reflectance? And they're both important, but the fact is so you can have where your optical light level is coming in, but your reflectance is very high. And whether it could be caused by the front end patch panel, it could be caused by any of the location where we get Fresnel reflections, but it's affecting the ORL, which is affecting your signal quality. And that can definitely be a problem. And that a question. Do I have experience with expanded beam connectors, and does it behave as an optical? I think you meant isolator there. But my experience goes back with expanded beam connectors. Most of them have anti-reflective coatings on them, and they're intended to reduce Fresnel reflections on it. You would have to check with the manufacturer of the connector and ask them what their Fresnel reflection values are for theirs. But I'm pretty positive that all of them use anti-reflective coatings on those. Do be careful of the cleaning materials that you use because of these coatings, though. The manufacturer may have very specific recommendations, because we don't want to damage those coatings on those. A question, does intermating APC and PC polishes cause damage? In other words, an angled physical contact and a spherical contact. We did measurements here and looked at them on interferometers, and we did not see damage occurring. That doesn't mean that all the manufacturers that would or would not. In one case, it makes sense because it is angled, but at the same time, the angle would be outside of the mode field diameter. I could recheck that again, but I believe we did this several years ago, and we had no case of it. But I hate to say 100% we could be positive on that. I'd like to get back to you on that. I'll just have one of our technicians retest that, and we'll look at it visually for it. Question, what should the length of your launch box be before and after your bulkheads? Again, the standards specify that the launch box should be 20 times the pulse width of the OTDR. So if the minimum pulse width was the equivalent of 10 meters, then we'd need a 200-meter dead zone box. And the reason for this is the pulse width is not exactly the amount of the dead zone. We have the tailing effect as well, and so the direct pulse width is not the same as your dead zone, and that the dead zone is normally much higher than that. Okay. Let's see, I'm not sure I understand this question. What is the difference between testing fiber cable physically and testing fiber cable speed? I know that, when we talk about testing a fiber, we're normally talking about attenuation testing and distance testing, and that using the OTDR, maybe the optical light source and the power meter. And that, so we're focused on that, on attenuation. But when we start talking about a data rate, reflectometers, OTDRs, they do not measure the data rate of it. So we're talking normally to understand data rate, we're really talking about the effects of optical dispersion, and whether that's chromatic dispersion, waveguide, including waveguide material, or whether it's polarization mode dispersion on single mode, modal dispersion on multi-mode systems. And in that case, we would need to be looking at an eye pattern or a bit error rate. Eye patterns are much faster, and as we're seeing more of a tendency to look at eye patterns to get quick go, no-go criteria. Let's see, a question on, is there a reason to test reflectance on both ends of a short patch cord? Well, one thing, if I'm buying patch cords, I would be checking on the manufacturer to verify that they are actually testing for attenuation and reflectance. And most manufacturers, quality manufacturers of patch cords, do provide this testing, but you really need to check. And we're fortunate here that we have interferometers, so that if we needed to and we were having a problem with a Fresnel reflection on a patch cord, we can actually look at the profile of the fibers in-faced and say, is the polishing causing a problem? Is it under-polished or over-polished, and so forth? If you're not familiar with interferometers, they're basically our check instrument for connectors that really allows us to look at the end face and the polish of that end face in detail, where an inspection scope will not give us that amount of detail. Okay, a question on when does chromatic and phase modulation distortion become problematic? In this case, we're changing from attenuation on the vertical scale and reflectance on a vertical scale to dispersion on a horizontal scale. In other words, how the pulse is actually being distorted. And so it depends on the type of fiber. I'm going to assume single mode here because of the question, and chromatic's much a major impact. And it depends on the distance of the fiber. It depends on the spectral width of the laser, and again, the modulation format that you're talking about. If we're talking about polarization mode dispersion, the greatest effects are above 10 gigabits per second to about the 40 gigabit per second area. The 100 gigabit systems, because they're using forward error correction and coherent detection, these are pretty much mitigated most of the PMD effects, but the importance of chromatic dispersion values are still great. Okay, if APC is a better connector, why today is a lot of networks still using SPC or UPC connectors? One is a lot of the systems were put in, and remember, most of these systems were digital systems, and those at that time, and again, when SPC systems were installed, we were pretty much at the level of 2.5 gigabits at that point. So we were running from the OC12 to the OC48 levels in the Sonnet world as a digital signal. So we could get by with an SPC or UPC connector at the time. Today, the speeds are much higher, and not only that, but those fibers now are using a lot of them are being used for DWDM applications, so dense wavelength division multiplexing. So we have a lot more wavelengths, a lot tighter together, as much as tight as 0.4 nanometer separation. And we're running optical amplifiers. So the importance of the reflections is we need to reduce them as much as we can. And even the EDFA amplifiers have optical isolators at each port on the input and out port to reduce reflections on those amplifiers as well. there's a question here, what considerations should be taken when using Raman amplifiers? Well, a couple things. One, when we're using Raman amplifiers, besides the safety issue that we're moving from class 3 to class 4 laser safety levels at times, we have some real issues and that. So I'm going to answer the rest of this offline because we are literally at the end of our presentation, and there's a lot of questions, a lot of great ones. I missed a lot of them. I apologize, but I will be getting back to you with those. So let's go to our closing slide here. We're going to readdress a favorite topic, emergency restoration. We're working on updating our emergency restoration courses right now, so I'm really excited on this presentation for July 20th. So we're going to talk more about some fundamentals and some real issues out there and some real challenges. So I look forward to have you participate. I apologize for the questions I didn't get to. I will be in touch with you personally on those as soon as I get the question list. Okay, so thank you all for attending and have a great day.